do me sitting at the laptop here, or I could sort of move over to the screen. I don't know which would work best. But,
okay.
Yeah, this is okay? Okay, excellent, great. Okay, very good. I will share my desktop. You can hear me okay?
Yes, we can.
Wonderful. Okay, good. Good. Okay. My presentation is actually going to follow on from Carl's presentation and pick up some of the concepts that he introduced already, and sort of embellish a bit more on those and stress the importance of modeling the correct physics for lightning, such as diffusion, which Carl mentioned, joint leakage. I'm also going to talk about cable transfer impedance for lightning assessment as well. So this is the outline of my presentation. I'm just going to start with a very brief introduction, and I think you probably all talked a little bit about the fundamentals of lightning quite a bit today, so I'll try and keep that very short, but it just helps, again, emphasize some of the concepts that I want to discuss in this presentation. Then I'm going to move on and go into panel diffusion in some detail, and explain how we can simulate that in both the time domain and also the frequency domain. We'll then move on to discussing seams and joints in structures and enclosures, and how we can efficiently handle this kind of detail for lightning analysis. And then we'll discuss the modeling of cables, and in particular today I want to focus on a little bit on cable transfer impedance extraction. In many cases the cable transfer impedance is unknown, and you need to have some way to try and determine that. So we can actually use simulation to extract the transfer impedance, which I'll show you. Then we'll just finish up with a few lightning examples. So just starting with some of the fundamentals again, but not laboring on this too much. So I think we've all seen that lightning is a transient effect. Really, it's a transient current effect. The lightning strike produces a very high intensity transient current, and there are various models for that current, such as the mill standard 464 definitions, the DO 160, and other standards as well. And I think you've seen this graph plot several times today, but this is the severe stroke or component A, as used in mill standard 464, where we have a peak current of 200,000 amps, and the current rises in about a microsecond or so, but very importantly, it takes a long time for that current to dissipate, many tens of microseconds or even milliseconds, for the current to dissipate. So it's sort of a slow, transient kind of phenomenon. Being a time domain effect, it's kind of natural to simulate this directly in the time domain using CST's transient solvers, either the TLM or the FIT solvers can be used for this class of problem. Looking at lightning from a frequency domain point of view, it's really a relatively low frequency problem. Most of the energy is below 10 megahertz, as shown in this slide. Yeah, and the wavelengths are correspondingly large. Okay, and that's good news from a modeling point of view, because if the wavelength is large, it means that we can use a coarse mesh, and we can cover large distances with a small number of mesh cells. That's the good side of modeling lightning, if you like. The downside is that because of these slow transients, it's really important to try and maximize the time step value. If we're trying to follow a waveform that is microseconds or milliseconds long, but we have a time step of picoseconds, that's not going to work too well. Okay, so one of the key modeling issues here is trying to maximize the time step value. And I think in CST's tools we have some nice ways to do that, which I'll talk about. Another key point that Carl just mentioned really is that oftentimes in lightning we're really focused on magnetic field coupling. The wave impedance, particularly near to the lightning channel, is low, maybe a few ohms or tens of ohms, and the magnetic field is dominating, and we really need to make sure that we're capturing magnetic field coupling to things like cable loops. Loop areas are very important. But also diffusion of the current through the panels and skin of aircraft structures or other structures is really critical. And Carl kind of showed something similar to this. This is a sort of relatively simple model of a lightning channel. As Carl mentioned, it is important to perhaps place a shield around the driving point, which is at the top of the channel in this case, and that ensures that the electric field that's directly generated by the source is shielded. And as a result, we see low impedance fields nearby to the channel. And it's one good idea, and I totally endorse what Carl was saying. It's good to start out with simple models, understand the physics of what you're modeling, gain confidence on something simple before you jump into the deep end on a really complex problem. I think that's a really good approach in general. So here what we did was we just simply modeled the channel, and we monitored the field at different distances away from the channel at 1 meter, 10 meter, and 20 meters. I'd encourage you to do that as well to make sure that the wave impedance looks reasonable. We can play a little time animation. So we can see as we drive that current into the channel, how does the magnetic field expand around the channel. So this is a true time animation. And what I'm doing is I'm kind of clamping the range, the scale for the magnetic field to 10,000 amps per meter, so that anything that's shown red here is 10,000 amps per meter or higher, okay? So, I mean, you can visually see that, within a few meters, tens of meters even from the channel, we're dealing with very high amplitude magnetic field strength. So it's always a good idea, I think, just do a simple model of a channel and understand the fields and just kind of get your head around what's important to model here. So we've just explained that lightning is a low-frequency, sort of magnetic field-dominated kind of problem, and whenever you have that kind of problem, diffusion is really important. Just very briefly here, I think we all know about the skin depth effect. When you have an electrically thin panel, if it is less than 1 skin depth thick, the current will diffuse through the thickness of the panel and arrive on the inside face of that panel. So that's an important coupling mechanism for lightning. For example, a 1 millimeter aluminum panel has a skin depth cutoff frequency of 14.5 kilohertz. That means that all frequencies up to 14.5 kilohertz will essentially pass through that panel. And you can see the formula for the skin depth. I think you're probably all familiar with that, shown in the slide there. But to note, the skin depth is kind of inversely proportional to the square root of frequency. And that means actually that often when you look at the coupling versus frequency, you see a sort of 20 dB per decade kind of change, variation. And that's related to that 1 over square root of frequency. Okay, and you'll see that in some of the results that I present later on. But again, it's always good to have those kinds of numbers in your mind and check the results to make sure they make sense. Can you believe that these results look reasonable? So 20 dB per decade is a good number to have in mind. Then on the right-hand side there, you can see the skin depth cutoff for various materials. So a 1/4 millimeter thick aluminum is 23 megahertz. So virtually all of the lightning spectrum will pass through that panel. So in order to attenuate, we need to make the panel thicker or increase its conductivity. And several speakers today have talked about composites and graphites, and one of the key issues with graphite is that the conductivity is lower than good metal conductors like aluminum. So for a 1 millimeter graphite panel, the cutoff frequency is 12.6 megahertz. So again, 1 millimeter of graphite virtually passes the entire lightning spectrum. And we can simulate that in the time domain. I'm sort of focusing a little bit on the TLM solver here, but we do provide FIT and TLM capability within the Studio Suite. The TLM solver does offer a thin panel model, which allows you to simulate the diffusion effect without meshing the interior of the panel. Okay. Now the key point about that is that, again, for lightning, we're trying to maximize the time step. So if we had to go in and mesh the inside of the panel, we'd have to use a very small cell size and a correspondingly small time step. So it'd be really difficult to solve this, even this simple panel type of problem. But fortunately, we have this thin panel capability. And so, simple test case, we could have a stainless steel panel here. subject it to an incident wave, and monitor the field just a few 25 millimeters behind the panel. This panel is 1 millimeter thick in the first case, and you can see on the right-hand side here that the magnetic field behind the panel is quite low. It's actually microamps per meter, given a 1 amp per meter incident wave. So you might think, okay, you know, it looks like maybe there's 100 dB of shielding there. Why would this be a problem then, you know, to have a 1 millimeter thick panel? Yet the problem occurs when you start to have two panels, you know, to make an enclosure. Because what happens is the current will diffuse through the first panel, but it gets trapped between the two panels. So with time, the magnetic field builds in this cavity that's formed between the two panels. And this leads to very significant magnetic field strength inside the enclosure. And that's why we really need to be concerned about magnetic field attenuation or shielding for enclosures subjected to lightning effects. So you can see here, you know, for 1 amp per meter incident field, 1.8 amps per meter external field, because the 1 amp per meter wave reflects off the front panel, so it almost doubles up on the outside. But we can see that we have about 0.1 amps per meter on the inside, so that's no longer 100 dB attenuation, right? It's a significant field inside the cavity there. Again, just like Carl, I encourage you to do simple tests to make sure that the physics is being modeled correctly before you jump into something complex. This is a rather nice, simple validation case. It's a stainless steel cylinder, length of 6 feet, diameter of 16 inches. Sorry about the US units here. The thickness is 0.5 inches and conductivity of 1.38 megasiemens per meter. So we can subject the cylinder to a direct lightning strike by attaching a wire to one of the end caps of the cylinder. And then we can use one of the features in the Studio Suite is a voltage monitor. You can define a path over which you would like to integrate the electric field to determine the voltage. We can use, there is an approximate analytical model for this diffusion case of the cylinder. I've given the reference on the slide there. And basically, you know, the coupling into the cylinder depends on the radius of the cylinder, the thickness of the material, the current that's driven onto the cylinder, of course, and the fall time and the wave shape of the incident lightning current. Well, this is the comparison between the TLM simulation and the analytical model, and you can see that for a 200,000 amp strike to the cylinder, we're predicting around about 13 volts developed inside the cylinder. So the simulation is agreeing nicely with the analytical results. So it's you know, it just helps you build some confidence again before you move to something more complex. Having validated the model, you can now play around with different thicknesses or different conductivities and see how that impacts on the voltage developed inside the cylinder. So, for example, if I reduce the thickness from 0.5 inches down to 0.039 inches or 1 millimeter, the voltage will increase from 13 volts to 270 volts. And notice also the shape of the induced voltage changes. Because the panel is thinner, higher frequencies can penetrate. So there's an earlier time response, a faster time response coming through to the inside of the cylinder. So that kind of makes sense. So it's a little bit about modeling diffusion. Very important to model diffusion, I think, for lightning applications. Another very critical feature, again, as Carl mentioned, is the modeling of joints or seams. You know, air gaps, like a slot or an open aperture in a metal panel, can be important for electric field coupling, capacitive coupling, okay? But for lightning, because we're often very concerned with magnetic field coupling, we need to be concerned with joints that have finite impedances, okay? So even if there is some conducting material in that joint, it still may not be a good shield for magnetic fields, okay? It might be a good shield for electric fields, but not for magnetic fields. So we need to consider these joints for lightning analysis. And we can oftentimes talk about a transfer impedance for the joint, which basically says that if we have some kind of current flowing on one side of this joint, so here you see actually the gray here sort of represents two aluminum sheets with some kind of conducting material in between, like a gasket, for example, shown in red. So for some kind of current flowing across that joint, we will develop a voltage across the joint, and that the relationship between the current and voltage is the transfer impedance. And in the studio, we can define a joint transfer impedance directly, okay, and apply that to what we call a compact model of a seam. So you can draw the path of the seam and then apply a transfer impedance to that path. And then that allows us to very efficiently simulate the magnetic field attenuation or shielding. So for example, again, just keeping things simple for now, we just take a rectangular enclosure, maybe a 50 by 50 by 25 centimeter box, and we drive the box with an external loop to generate the magnetic field, and then we use a loop to measure the internal magnetic field. We can do this. We can use this to compute the magnetic field attenuation. So the idea is that you would first model the two loops without the enclosure present, and that gives you a reference. And then you place the enclosure between the loops, repeat the simulation, and then you can use the reference to normalize and extract the shielding performance. Okay. So for a enclosure that has 1 millimeter thick stainless steel walls, you can see that the magnetic field attenuation is around about just over 20 dB at, let's say, 10 kilohertz. And there's the 20 dB per decade characteristic you can see in the results here, which is associated with that skin depth behavior that I referred to earlier. So, you know, it's a good sanity check, again, that your model is behaving as you might expect. Eventually, when we get to very high frequencies, the box goes into resonance because it becomes more electrically significant. Okay, so we could then maybe add a seam to the box, a joint. So the blue line at the top of the box on the front panel here is actually the path of a seam. And we can apply properties to the seam, such as conductivity, the overlap between the two metal panels and the gap width. This can all be done in the electrical model of the seam. It's not necessary to model this geometrically and use a fine mesh to capture the small dimensions. Again, this is really critical for lightning because we're trying to maximize the time step. So these equivalent models are very, very useful from that point of view. In order to just look at the effect of the seam, we could make the enclosure walls perfectly electrically conducting. So we kind of switch off the diffusion effect through the skin of the walls. So we're just focusing on coupling through the seam. And, you know, again, the analysis shows the typical behavior that you would expect for this kind of problem, the 20 dB per decade characteristic. And you can also see that if I increase the conductivity in the seam, I can improve the shielding effectiveness by maybe 10 dB or so at low frequencies. That diverges at the higher frequencies, as we'd expect. It's just a little animation, just again to sort of verify that everything was set up correctly in the model. I can see the magnetic field vectors kind of cutting through the loops and inducing voltage inside the loop on the inside of the box there. The seam actually looks like a rather large gap at the top of the box. That's just a visual effect. In reality, it's modeled, you know, with some very small dimensions of overlap, and there is a conductivity in that joint. So, you know, having applied the modeling to some simple benchmarks, you would then build up the complexity and maybe look at a more realistic enclosure. This is an avionics line replacement unit, and we could import this geometry from a CAD file, such as a SAS file or STEP file, IGES file. One of the nice features we have in the Studio Suite is the ability to convert solid bodies into thin sheets. And that's important because it then allows us to treat those thin sheets as diffusion boundary conditions, okay? So again, we do not need to mesh the thickness of these walls of the enclosure. We can use a special diffusion model to simulate the coupling to the inside of the enclosure. So one simulation that you might do is to drive current onto the connector interface, the connector panel, by attaching a wire to the connector, to the shield of the connector. And then maybe you might be interested in the the coupling due to a finite impedance for the joint between the connector panel and the enclosure itself. So these are kinds of things that you could study and understand. What kind of impedance can I tolerate, for the interface between the connector panel and the enclosure? For this kind of problem, we may still wish to refine the mesh to capture some of the geometric features. So the hexahedral mesh will refine in different regions, but a feature called lumping can be used to lump the fine cells together into bigger cells as we move away from those boundary conditions. So the background mesh uses about 1.38 million cells, but through this lumping process, that's reduced down to 72,000 cells. So that's a huge reduction. It's about a 95% reduction in cell count. Again, really important for lightning type of problems, because you want the computation per time step to be minimized, okay? Because to cover these long transients, we may have to compute many time steps. So we need to do as little computation per time step as possible. So that means keeping the cell count down to a minimum. So, these features, I think, are very relevant to lightning-type problems. So to cover the full lightning response, we would compute 2.5 million time steps for this problem. The memory required is actually very reasonable, 55 megabytes, and we can solve the enclosure in about 4 hours on a typical desktop computer. So the results would look something like this. So we are modeling the diffusion through the panels, the coupling through the finite impedance joints, we run the analysis directly in the time domain, but we can then convert to the frequency domain and normalize our results to the drive current. So the drive current becomes 0 dB, constant 1 amp versus frequency. And then we can look at the magnetic field both behind the panel and at the center of the box. And where you can see at 100 kilohertz, we only have about 10 dB of shielding, to magnetic field shielding. So that's kind of interesting. We can also run an animation of the surface currents. So again, really I always use this to visually check that the model was set up correctly, that the current is flowing in ways that I might expect. So you can see the current being injected onto the connector panel, and it's forced to flow across that joint between the connector and the main enclosure. And as it flows across that joint, voltage is developed through the transfer impedance, which leads to this magnetic field inside the enclosure. But also over the whole front face of the enclosure, the current is diffusing through the thickness of the panel. So there's actually quite a lot of physics being modeled in this simulation here. This is actually an animation of 1 megahertz, and at this frequency, the current is going to try and take the path of least inductance. Okay, so it's kind of interesting that it mainly stays on the front panel, and it returns through the legs of the enclosure where it's mounted to the ground plane. Very little current is actually flowing over the side and top walls of the enclosure at this frequency. If we were to look at a lower frequency, the current may take the path of least resistance, and you would see the current flowing over the whole structure. Okay, so that was a little bit about modeling joints and seams. Now I want to just talk a little bit about cables. And Carl, actually this is directly one of the slides that Carl showed, and I'm just using this as a reminder that one possibility is to model cables using a thin wire approximation in our 3D solvers directly, and it is possible to convert a thin wire into a shielded cable representation, a screen cable representation, as Carl mentioned. And you can apply a transfer impedance to that thin wire, which allows you to solve for the inner wire current. So you can obtain the shield current and also the inner wire current. So this can be done directly within the 3D field solver. And Carl already mentioned that, so I don't want to labor on that point. And he showed a nice validation case comparing with a circuit model. But another possibility is to For more complex cable types is to use the Cable Studio tool, and I think you've already seen some presentations on this today. But I just want to remind you that you can define more complex cable cross-sections. What I'm showing here is a double-braided twisted pair cable, which I might be interested in, subjecting to a lightning event. So in Cable Studio, you can build up arbitrary cable types by using the basic building blocks, such as conductors, twisted pairs, and other building blocks. And then you can place screens or overbraids over those conductors. And Cable Studio will use Clay's formula to calculate the transfer impedance for the overbraid. So it will determine the transfer impedance directly for you within the interface there. And then we can use Cable Studio to do things like, in this case, I'm actually injecting a current on the shield of the cable. This is one of the lightning waveforms. It's a damp sinusoidal waveform with we have about 60 to 70 amps peak current on the shield. And Cable Studio can be used to predict the voltage that develops inside the cable. In this case, we see between 3 and 4 volts peak current developed inside the cable. So, Cable Studio is a great tool for looking at transient susceptibility problems for more complex type cables. However, in some cases, the cable cross-section could be more complex, and it may be necessary to actually use 3D simulation to extract the transfer impedance if the measured impedance result is not available. So let's just talk about cable transfer impedance a moment here, because it's very important. Lightning current can diffuse through solid cable shields and induce voltages inside the cable. And you can see here that Carl actually referred to the DC resistance. He said it's very important what level the DC resistance is for the transfer impedance. And that can be calculated using this equation. It's inversely proportional to the radius of the shield, the thickness of the material, and the conductivity. So we do just a little quick calculation here for a typical cable type, and with a 0.127 millimeter thickness, copper material, and about a 1.5 millimeter radius. This is actually Stavage 58 kind of parameters here. You can see that the DC resistance is around about 14 milliohms per meter. Okay. What happens is that if we then introduce braiding into the shield, we will have little apertures in the shield that will be important for higher frequency coupling. The braid has a finite optical coverage, and higher frequencies can couple through those little apertures. So there's two things here. At low frequencies, the current can diffuse through the shield, through a solid shield. At high frequencies, coupling can take place through the little apertures in the braid. So one thing that we can do is we can use 3D simulation to actually predict transfer impedance. And the way that we do that is by forming a triaxial configuration. The cable is modeled inside a further cylinder that is used as a return conductor for the current. So we're able to use a port here to drive current down the shield, return it through this third cylinder, and as the current flows over the shield, it couples through to the inside of the cable, and we can use a voltage monitor inside the cable to detect the induced voltage. So if we look at the typical result from the 3D simulation, you can see here the time domain response of the voltage developed inside the cable. And again, you can see that kind of filtered effect due to the skin depth and diffusion, this very characteristic kind of time domain response that we see inside the cable. If we Fourier transform and look in the frequency domain and calculate the transfer impedance from the current flowing on the shield and the voltage on the inside, you can see that the simulation is predicting almost exactly 14 milliohms per meter, as theory would suggest it should be. But notice also that the simulation is correctly predicting the reduction in transfer impedance due to the skin depth effect. Okay, so that's, again, a nice validation case for the modeling, and shows or proves the case that we could use 3D simulation to actually extract transfer impedance of cables. Furthermore, in the 2011 release in Cable Studio, you will now have the possibility to import either measured data for transfer impedance or simulated data. So I took the transfer impedance that I just pre-calculated, in 3D. I imported that into Cable Studio, the 2011 version, and you can see the imported transfer impedance, which you could then apply to your cable model. So this is a really nice new capability that's coming along in 2011. Really extends, I think, the range of applications that can be used for Cable Studio. You can even go further with this and actually build a 3D model that includes the braid apertures. We can kind of take a rhombic-shaped aperture, and we can copy and rotate it around the cylinder to create all these little apertures, and then do a 3D simulation that can consider both the low-frequency diffusion and also the high-frequency mutual inductive coupling through the apertures, and use the simulation to determine the transfer impedance. We're actually working on some more sophisticated cables right now that have foils and spirally wrapped foils, and using the simulation to extract the impedance, because it's not always provided by the vendors. So if you're interested in that kind of problem, we can certainly point you to some more efforts in that area. So here's a very typical result for the sort of higher frequency part of the predicted transfer impedance. And you can see that at high frequencies, the impedance sort of steadily increases with frequency, and that's because the coupling is now through all those little holes in the braid. It's mutual inductive coupling. Okay, so what's also possible is to take a hybrid approach. We can combine some of the features I've been discussing, such as the diffusion modeling, the joint modeling that's available, for example, in the TLM solver. We can combine that with the Cable Studio tool and create a sort of hybrid approach. So you might consider, for example, we might model an aircraft, and on the aircraft we may have some finite conductivity panels, composite materials. We may have some seams around the doors and other joints, but the cable on the inside may be quite complex, and we wouldn't want to have to mesh the detail of that cable. So for the complex cable, we could use Cable Studio. In order to sort of validate this approach, we did a simple case where we had a thin wire, a 57-foot long wire inside the aircraft, and we modeled it directly using the thin wire in the 3D solver, and then we also modeled it using the hybrid approach with Cable Studio and compared the results. And you can see, if I inject a current on the nose of the aircraft and take it out of the horizontal stabilizer, and if I normalize the internal currents to the driven current, so 0 dB here means I have 1 amp versus frequency on the input current, you can see that Cable Studio, the hybrid approach and the direct thin wire approach, show pretty good agreement for the coupling to the internal wire. So that gave us some confidence that we could use this hybrid technique, and I'll show you some more realistic examples of that in a moment here. So just to finish now, I'm just going to show you a couple of examples, and then we'll draw some conclusions. The first example is a test case from the Air Force Research Labs here in the USA, where a cylinder was actually fabricated to represent a fuselage of an aircraft, and AFRL ran some tests, some lightning tests, to look at the coupling to the inside to a cable on the inside of the cylinder. And what they did was to do things like remove. The cylinder has a series of removable access panels, and some of those panels can be removed. Maybe 1 or 2 might be removed. They may be put back in place, and then the coupling is compared for different configurations. Now, in order to remove the effect of the ground plane underneath the cylinder, because that might cause the magnetic field to be non-uniform around the cylinder, a return conductor system is used to kind of balance the magnetic field to make it more uniform, but also allow the current to flow back to the generator. And we actually modeled that in the 3D simulation here. Here you can see some of the detail. You can actually see the access panels going down the cylinder. There are 16 in total. In order to model the the diffusion or the coupling to the seams around those panels, we use the compact joint model, and we can specify the gap width, the overlap, and the material, the conductivity in those joints using this equivalent model. And then inside the cylinder, you can see we have a 24-foot long wire, and we're interested in the current that is developed on that wire. So this is the simulated result. Two results here. The green result is when two of the access panels are open. The red result is when all the panels are closed. So you can see a reduction in coupling to the internal wire when we close the entire structure. However, there is, of course, some coupling because of diffusion, because of the leakage through the joints. What was quite nice with this is that the peak current levels do show some nice correlation with the measured peak currents, which were seen to be 12.3 amps with the two panels open and 2.6 amps closed. So some quite nice correlation between modeling and testing that. And here you can see, again, a visual of the magnetic field. You can see the field is quite uniform because of the return conductor system, but you can also see the magnetic field kind of leaking in around the joints around those access panels and ultimately coupling to the internal cable. The second and last example I want to share with you is really just going back to that aircraft model, but instead of using the simple thin wire, we now utilize the power of Cable Studio and model a more complex wire, in this case a sort of Cat5 cable that contains 4 twisted pairs. We can now use the hybrid approach to inject current onto the fuselage and predict the voltages or currents that are developed inside this more complex cable. Here you can see the magnetic field that is predicted from the simulation. The red result here is a monitor point that is external to the fuselage, so we see a large magnetic field of 12,000 amps per meter. The green result is a monitor that is just behind one of the doors. And the doors did not have a conductive gasket in this case, so high frequencies can kind of couple through that aperture. So you see some early time response in the results, albeit very attenuated. It's 1,000 amps per meter down from 12,000 amps per meter on the outside, but it essentially follows the lightning waveform. The blue result is at a point close by to a composite structure. Part of the fuselage is composite material, and for that part of the fuselage, the current essentially diffuses through the material. So you can see it takes some time for the current to arrive through on the inside of the aircraft. You get this very slowly varying response because of the diffusion effect. Now, Cable Studio, we can get down to the different pin voltages and currents, and this shows how we terminated the wires in Design Studio in the circuit simulation, and some of the voltages that are developed. And in the result that we see here, we can detect the cable resonances and the airframe resonances. We see a peak in voltage at 4.2, 12.4, 21 megahertz. And if you do a quick, back of the envelope calculation, you can determine that makes sense given the dimensions of the aircraft and resonances at half wavelengths and so forth. So finally, this is a little animation of the magnetic field in a plane cut through the aircraft. So on the right-hand side is the front of the aircraft, and you can see the magnetic field leaking in through the glass windows of the cockpit. There's sort of two red regions there, which is indicating strong coupling through the cockpit windows. A little bit further down, you can see the leakage through the door, through the front passenger door, and you can actually see a little bit of leakage through all of the passenger windows going down the fuselage, leakage at the door at the back of the aircraft. But in the middle here, where the wing box is modeled, in this case, is composite material, you can see that with time, that builds up due to this diffusion effect and leads to quite strong magnetic fields in that region of the aircraft. So just to summarize then, so we've been talking about lightning simulations with the CST Studio Suite. I mentioned that direct time domain analysis, I think, is very useful for this class of problems. It enables us to simulate the lightning standard waveforms directly, allows us to predict peak voltages and currents and the dwell times that are associated with the lightning strike. I think we have some nice features such as the thin panel model, the C models that allow you to efficiently capture some of the physics that's very important, the panel diffusion, joint resistance. The thin wire model and shielded cable model allows you to investigate common mode coupling to cable and circuits, particularly looking at loop areas and magnetic field coupling to loop areas inside the system. Cable Studio extends the cable modeling to more complex cable bundles, realistic cable types, and we can use this hybrid approach to mix the 3D field simulation with the Cable Studio modeling. And then finally, I showed something a little bit new today where we can use 3D simulation to predict the transfer impedance of arbitrary cable types. There's actually been a lot of interest in that from customers over here in the USA, so I gather there probably could be similar interest in Europe, but it seems that in many cases the cable transfer impedance is unknown, and folks need some way to try and estimate those impedances. So I think we have a nice workflow for calculating that, but also for, in the 2011 release, importing that data into Cable Studio and then applying it to your Lightning model. So with that, I just want to thank you for your attention today, and if there are any questions.
Thanks a lot, David, for this interesting presentation. Any questions?
You're welcome.
Seems people are ready to leave now.